Okay, Peter, you can go for it.
Okay. Yes. Hello. Good evening, everybody. And it's a great pleasure to welcome Stephen Potter tonight as our guest speaker. Stephen and I actually met a couple of years ago. I think it may be more than 2 decades ago, on a plane to Bloemfontein, where we were asked to act as examiners for an MSc student. And since then, a lot of water has flown under the bridge. Today, Stephen is the head of research at SAAO, and he's in a pole position to tell us about all the facilities and the research that they are currently conducting. And so, Stephen, please, we are looking forward to your talk and have fun. Thanks a lot.
Great. Thanks, Peter. Thanks for the introduction, and thanks for inviting me to speak to you today. I really appreciate it. Let me just start the slideshow. Okay, so as Peter said, I don't know if you said this, but I work at the South African Astronomical Observatory. I also have an associate position at University of Johannesburg as well, so that's why I also got UJ mentioned there. And so what I'm going to be talking about today, I'd just like to mention some other members of staff in the team that I lead at the observatory, so just to give them some acknowledgement there. And the topic of my talk is the Intelligent Observatory, and hopefully by the end of this presentation, you'll know all about what the Intelligent Observatory actually means. So as Peter mentioned, I'm the head of, well, he said head of research. I'm actually head of astronomy. It's a subtle difference. But as head of astronomy, my basic responsibility is to oversee the service of astronomy that we at the observatory give to our users of the observatory, the astronomical community. And so just to give you a quick reminder of what the South African Astronomical Observatory is. So the headquarters is based in Cape Town. And I'm in Cape Town at the moment. I'm talking to you from home in Rondebosch. But our observatory station is out in the Karoo, near about a 20-minute drive outside of the village of Sutherland. This is an aerial photograph of our site in Sutherland. You can see there are many telescopes there. I think we're approaching almost 30 different facilities there. In the background right at the right-hand side there's the South African Large Telescope. So that's one of the largest optical telescopes in the world. And then we have other telescopes. There's the hopefully, I think you can see my mouse moving. There's the 1.9 meter telescope, and then we have our there's two 1 meter telescopes and another telescope in there. And then we have a whole host of other we call hosted facilities. And these are either facilities that we are in partnership with another institute. So for example, this telescope over here is an infrared telescope, and that's jointly operated in partnership between us, the SAO, and an institute in Japan. And then there's another 3 telescopes here. Each one of these is a 1 meter telescope. This is part of a network, a world network of telescopes called the Las Cumbres Observatory. And that's a privately funded organization. It was actually funded by one of the founders of Google. He really liked astronomy, and he decided to fund a network of telescopes around the world. And so because we host some of those telescopes, we get a percentage of time on the whole world network of those telescopes. And there's a whole lot of other telescopes as well, but I'm not going to go into listing all the details of all those, but you get the idea. So we're approaching about 30 telescopes. And in fact, even though this image was made maybe 3 years ago, it's already out of date. We have another facility about there in the middle, a second joint partnership with an institute in Japan. And there's actually a little patch here where we also have another new telescope. It's a NASA, it's part of a NASA network. And I'll tell you a little bit about that one later on in this presentation. So as I said, my role as head of astronomy is to ensure that as a national facility, we provide world-class astronomical service to the astronomical community, whether it's national or international. And so one of the challenges of this position is to ensure that we provide up-to-date world-class service. So when I started this position, well, actually, I started this position about 10 years ago, but about 5 years ago, we decided that we needed to upgrade our service of astronomy to the community. So that's where we began this program called the Intelligent Observatory. How do I, there we go. So this presentation is divided into 3 parts. So I'll start just by quickly telling you what the vision, the eye, every time I refer to the IO, I'm referring to the Intelligent Observatory. So I'll start by saying what the vision of the IO is and the SAAO, what developments have been made since we started that program. And then probably half of the talk is actually on the science highlights that have come out as a result of the developments we've made since we started this program. So let me elaborate on what the vision is. Sorry, there's only maybe 2 or 3 slides that are bullet point slides, so don't be put off by bullet point slides. This is only one of, I think, 2 or 3. But I wanted to just stress what the vision is. So that in one sentence, the top level vision is basically to better serve the community of users. And the challenges that we gave ourselves was we want to be able to allow our astronomers to submit science proposals at any time. Now, if you've ever used our facilities, you know that if you want to use a telescope, there are certain calls made 2 or 3 times a year in which you have to submit a scientific case to use one of our telescopes. And it's a competitive application process. And that only happens maybe 2, sometimes 3 times a year. We want to break out for that and break out of that and allow observers to submit proposals anytime. We want to be able to allow scientists to do science on any time scale. So the challenge here is that in the past, if you wanted to use our telescopes, once you get awarded your time, you're told at what week in the year you have been allocated, and then you would travel to Sutherland, spend the week there to make your observations, and then come home, and then go home. So we wanted to break out of this constraint as well. We don't, it's a bit constraining to your science has to fit within 1 week of telescope time. And traditionally, it's been 1 week because that's basically the kind of minimum time slot that you'd want to spend away from home by taking the trouble to travel to Sutherland, have enough time in Sutherland to get some good weather, and then do your science to come home. But there are some science programs where it just doesn't fit into 1 week. You might only want to do a 10-minute observation, or you might want to do 10 minutes once a week for a whole year. So programs like that were not possible to do on this traditional 1 week timescale. The next challenge we gave ourselves was we wanted to allow observers to not only be able to observe from Sutherland, but also observe from Cape Town or indeed from anywhere else in the world. So eliminating the possibility, the requirement of traveling to Sutherland in the first place. We also wanted our observers to have more flexibility in how their observations are obtained. So in addition to manually operating the telescopes and instruments, we wanted to introduce a queue or service type modes of observations as well. Another challenge is that we want to be able to allow our telescopes to automatically respond to alerts or computer-generated requests. And I'll explain what that means a bit later on. And then one of the biggest challenges is to look at the whole pipeline from, you know, where a scientist, an astronomer has an original idea, and then, you know, they submit a proposal, they get their observations, they acquire the data, they reduce the data, and then eventually your data gets to a publication. So we wanted to look at that whole stream to see how can we help our users in every step of that process to get to the publication as soon as possible. And so all this basically adds up to also that we want to enhance basically our national and international partnerships. So that's our vision. And what it actually is therefore that we want all of our telescopes integrated into a overall kind of intelligent observatory. So at the moment, all of these facilities, they're all kind of independent, and instead we wanted the outside community to see the SAAO as providing an astronomical service, and they don't need to worry about details of, oh, which telescope should I use, which instrument is where, and all that sort of thing. So we wanted to be a bit more intelligent in that, and basically we would do the coordination of the science across all of our telescopes. Our users wouldn't have to worry about that. And basically, to solve all this, we would build upon modern day communication technologies, automation, and intelligent algorithms, and maybe artificial intelligence, and basically advancing the SAO into the so-called fourth industrial revolution. So that's our vision, and that's our list of challenges that we set up for ourselves. So now I'm going to race ahead. That was a challenge. So where do we stand today? So as I said, we have a whole mixture of telescopes, but there's 3 of them that you remember I said many of them are partnership telescopes, but there are 3 telescopes that we fully own. They're fully South African, and we maintain, operate, and develop the technologies on them. So we decided to focus on these 3 telescopes first, and have these to be developed to be the core service by which everything else would be intelligently connected to. And within these 3 telescopes, we can basically provide every mode of astronomical observations that you can imagine. So between the 3, we can do spectroscopy, polarimetry, normal imaging, or high-speed imaging. So all those combinations is available through these 3 telescopes. So as of about 5 years ago, if you wanted to use any of these 3 telescopes, you would have to spend 1 week in Sutherland to use them. But as of about 2 years ago, we've upgraded all 3 telescopes such that they can now be remotely controlled from anywhere in the world. So this involved a lot of hardware upgrades and a lot of software upgrades. So now users of these telescopes can actually choose to still go to Sutherland if they want, but now they can also remotely operate them from anywhere in the world. So this was quite a technological feat, I think, because this middle telescope was probably the easiest one to do because it's one of the newer ones. But the 1 meter telescope on the left is over 50 years old. And our largest telescope, well, besides SALT, is our 1.9 meter telescope. And this telescope I think is now over 80 years old. But all 3 telescopes technology-wise are now at the same level. They provide the same astronomical service in terms of modern-day instrumentation and the mode at which you can operate them. And because now that we can offer these telescopes to be operated remotely, it means scientists, observers are no longer restricted to making their science fit within those 1 week slots. They can now just ask for, I just want the telescope for a couple of hours, or I just want the telescope for a night, or I just want the telescope for one night, every night, sorry, 1 night per month for the rest of the year. The floor is now open. They can do all those sort of scientific programs or ideas that they couldn't do before. So that's the state we were in as of about 2 years ago. So the next step now, fast forward now to about this time last year, is we next focused on our newest telescope, our 1 meter telescope. And we're now at the stage where this telescope is now fully robotic. So you don't have to even, not only do you not have to go to Solomon to use this telescope anymore, you don't even have to use it remotely. You can now submit observations to this telescope via a web interface. So this was probably our biggest technical challenge, and I should stress here that this is all the development work was done in-house. So all the hardware upgrades to make this telescope fully autonomous, and also all the software upgrades was all done in-house at the SAAO. So as I said, this is probably the only other slide that has bullet points. But basically, this list describes what is it that you have to do to a telescope to remove a human from operating it. So you can imagine there's all the low-level functions you have to do to operate the telescope, from simply pointing the telescope to where you wanted to point it to, and then, you know, as a human, once you think you're on target, you then look at an image and confirm, are you on target or not? So we have to replace that with some clever algorithm that analyzes the image and determines where the telescope is accurately pointing. And then, you know, if you're operating the telescope and you look at the live image, you then gradually nudge the telescope so it's exactly pointing where you need it to do. So we had to develop algorithms in order to do that. In particular, especially for spectroscopy, where you have to accurately put your telescope on the slit of the telescope. So it has to be pointed to an accuracy of an arc second or better. So all that fine tuning that a human usually does, we've now automated all of that. And then, of course, there's identifying a guide star and performing guiding. There's configuring the instrument appropriately, whether you want to do imaging or spectroscopy. And then, of course, you have to adjust the focus as well. All that's now automated. And then, of course, making exposures. And, of course, the other thing an astronomer does at the telescope is that they keep a log of their observations, right? So we have to automate all that. So the software collates all the necessary information that you as an observer would do. You know, you would note down the weather conditions, all the telescope parameters, where it's pointing and all that sort of thing, what configuration the instrument is in. All that then is collated and bundled together with the data that's automatically taken. So that's kind of the low-level stuff. But then the other thing we had to develop as well was a higher-level software on top of that that takes care of, well, what shall it observe tonight or any other night, actually? And that's what we call the OCS. So this stands for the Observatory Control System. And so this is one piece of software that we didn't have to develop from scratch in-house. we were very fortunate, actually, that at the time that we decided to develop this software, the last Crumbus Observatory that I noted to you earlier, because they were privately funded, their funder said, whatever software I fund, I want you to open source. And they developed a whole observatory control system software package, and they open sourced it. And we were the first observatory to seriously take a copy of that software and configure it for our telescope. So this saved us maybe 10 years of software development, and we were able to configure this for our telescope straight away. So as I said, the function of this piece of software is one, to present an interface, a web interface for all users of the telescope to submit their observations, so that gets put into a queue. It also tells them when their observations are queued for, and when their observations are being completed and their data is ready to be downloaded. It also manages the queue of observations, so that it works out what time of night particular observations requests can be observed, and also it prioritizes them as well, depending on certain priority factors that we give to each science program. Yeah, so that's that. And the other important feature about this observatory control system is that you can what's called programmatically submit proposals to the queue. So you don't even have to be a human being to submit an observation to this. You can write a separate piece of software that, we allow, the observatory control system allows requests to come in through the internet via any means whatsoever. So it can be some intelligent automatic software anywhere else in the world that's perhaps waiting for an alert of some sort. Maybe a supernova explosion's gone off, and instead of having a human to submit a proposal, it will programmatically just submit an observation request directly to the OCS, and then it will get put into the queue for observations. Okay, and then at the other end, at the final end, at the data product end, we've also now developed rapid response data reduction tools. So we've already developed a web interface where, as soon as a spectroscopy has been made on the automatic telescope, within 1 minute we make available a fully wavelength and flux calibrated spectrum that can be accessed through a web interface. So this is a spectrum of a supernova. It was just a few weeks ago, actually. I can't quite see that. 15th of June, I think. This was a supernova. So this was an automatic alert that came in. So at the bottom there, you got a fully flux calibrated spectrum. But in addition to that, you get the acquisition image. So you can see here, this is the associated galaxy with the supernova, and you can see there that bright star, new star, is the supernova in this galaxy. So you get this acquisition image, and then it draws on here where the slit is for the spectrograph. Sorry. So you can double check that the star, the telescope did indeed accurately position the star on the slit. And then this is the raw spectrum image that you get. So you can see there's the spectrum of the supernova, and you can see some other emission lines from the background galaxy. Yeah, so that's where we are there. Sorry, so now I've moved on to the science highlights of my presentation, if you didn't realize that already. So in addition to software upgrades, we've also, as I mentioned earlier, we had to do a lot of hardware upgrades. So to make a telescope fully autonomous and or remotely controlled or fully autonomous, it's not just software, it's also a lot of hardware as well. So everything from simply turning power on and off to the whole facility, to opening and closing the dome shutters, the mirror covers, all those sort of things required the development and the installation of hardware to make that happen. And that was all designed in-house in our workshops and designed and then manufactured and deployed. But earlier this year, we also commissioned a, what did we call it? An instrument selector port. So we recognized, so for example, on our 1.9 meter telescope, we actually have 3 instruments available. A polarimeter, a spectrograph, and an imager. But the problem was that only one instrument could be mounted on the telescope at any one time. And to change from one instrument to another would require perhaps half a day's work of a team of 4 people to perform the instrument change during the daytime. Because of that, instrument changes were limited to maybe 4 or 5 times per year. And we recognized that if we could at least mount 2 instruments at the same time and allow the user to switch between, say, just imaging and spectroscopy, that would be a massive upgrade for the 1.9 meter telescope. So this idea of an instrument selector port, we came up with maybe 2 years ago. And again, it was all designed and manufactured, and then eventually it was deployed in January of this year. So now we have 2 instruments on the 1.9 meter telescope at the same time, basically the spectrograph and the high-speed imager. So now this allows the observer, the user, the ability to choose to switch between either spectroscopy or normal imaging as many times as they like during the course of a night, rather than now, the change having to be made by a team of 4 technicians, maybe 4 or 5 times a year. So this was deployed, as I said, earlier this year. And, okay. I've already gone to science highlights, but now I really am going on to some more science highlights. So now having deployed this is one of the first science. This is actually the first science highlight from the instrument selector port. To give you a good example, so on the 21st of March 2024, so this is about 2 months ago, March, I think 3 months ago now. Well, actually, earlier this year, the Japanese launched a new X-ray telescope. It's called the Einstein probe. And within a few weeks of it being launched, it was already discovering new X-ray sources. And on the 21st of March, this is one of the first transient X-ray sources it discovered. So this was a new X-ray source. It was released as an astronomer's telegram notice. So we receive these telegrams as soon as they're released. So on the 21st of March, the Einstein probe released, as I said, a new transient X-ray source. So we followed this up with, we were able to point our 1.9 meter telescope at this source within 2nd of April. So this is about 10 days later. We were able to get a nice photometry light curve of it using the new actually imager on the instrument selector port. And you can see from this that it shows kind of a long-term variability, but you can also see that there's a very high frequency variability on there as well. And so we've identified 2 frequencies or 2 periods in the system. There was and I can't remember the numbers now, but there was the high frequency has a period of about 4 minutes, and the longer period is about 4 hours. So we identified this as some sort of potential, maybe a cataclysmic variable of some sort. But with our instrument selector port, we were also able to, within a couple nights, then just switch to spectroscopy at the flick of a switch. And we were able to get spectroscopy. And it's from the spectroscopy, actually, that we were able to identify the orbital period of the system just by looking at the kind of radial velocities that you can see in the trailed spectroscopy from this source. And it was from the photometry that we could see that high frequency variations that I showed you in the previous plot. So as I said, this is quite an interesting system because with an orbital period of 4 hours, this is obviously a compact binary of some sort, but also the 4-minute spin period of the white dwarf is also quite interesting because this is one of these kind of fast spinning white dwarfs. And so we're still not quite sure what this system is. We initially identified it as what we call an intermediate polar, but now we're not so sure because observations we obtained just a few nights ago has changed our picture slightly. What we do know is that it's a compact binary. So one of the stars is a red dwarf star, and the other one is most likely a white dwarf star. And we think there is signs of accretion in this system. But also there's a lot of flaring activity in this system as well that we've seen in the spectroscopy. And also the orbital period and the fast spinning white dwarf, those two frequencies put this object in the same class of a new class of object that was only discovered 3 years ago called white dwarf pulsars. The spin period and the orbital period, the parameters are absolutely almost identical. And the only difference is in this system, there appears to be a bit of accretion going on. So this is kind of a picture of maybe what's going on in this system. So there may be some accretion going on, maybe an accretion disk or ring of some sort, maybe some magnetic interaction with the magnetic field of the white dwarf with the secondary star, and maybe there's flaring activity on the secondary star that's interacting with the magnetic field of the white dwarf, and maybe there's some synchrotron emission coming from the magnetic poles of the white dwarf as well. So we think this is one of the systems that has all of these things happening at the same time. So it's quite a nice discovery for a first science from our instrument selector port. But the other thing I want to highlight from this discovery as well. So this is the paper. This is just the front page of the paper that we wrote after this discovery. So if you just look where the arrows are on the bottom right, as I mentioned earlier, the Einstein probe announced that this is a new X-ray source on the 21st of March this year. By the 2nd of April, we'd obtained, so within maybe 10 days, we'd already attained spectroscopy from the 1.9 meter telescope and photometry from the 1.9 meter telescope. And also we've got, I didn't mention this, but we also got spectroscopy from SALT as well. So by the 2nd of April, we'd then written the paper in record time. So within 2 weeks of getting the final data, we had written the paper and submitted the paper. The paper was then accepted 10 days later, and by the 6th of May, the paper was already published. So this is a new record for us. Generally, it typically takes at minimum maybe 3 months after you've obtained your data to have a draft version of a paper ready, and then maybe up to 1 year or more until you eventually get a final submitted paper. So we did this in record time, And so I'd just like to explain a few reasons why I think we were able to do that. So one was we were able to respond to this alert straight away. We were able to submit our observation requests straight away to get time on the telescopes. We didn't have to wait for the call. So that's one of the objectives that we've implemented and taken advantage of. We were then able to get spectroscopy and photometry very quickly. We didn't have to wait, when in that 4 or 5 times per year would the instrument be changed for us. We were able to do that straight away. And then the other thing, you'll notice that I'm the first author here. So I wrote this paper, and one of the reasons why I was able to write this paper very quickly, well, I'm going to give you 2 reasons. One is, as I showed you earlier, we now have data reduction pipeline that reduces the data very quickly. So we were able to have reduced data very quickly. The second thing is, the one thing that I've been particularly slow at throughout my whole astronomical career is actually writing papers, is getting down, sitting down, and actually writing. So I'm going to admit to you here that I use ChatGPT to help me write this paper. And it's absolutely astounding how ChatGPT just takes my poorly written content and translates it into professionally written content. And this speeded up writing of papers by, I don't know, a factor of 50, perhaps, to be realistic. So yeah, so that's how we got this paper out really quickly in the end. And we just check the time. Oh, good, we're doing well. Okay, so just to give you a couple more highlights. So another project we're involved in, which we weren't able to do before, but we can now, is the following up of near-Earth objects. So near-Earth objects, for example, can include asteroids that come close by Earth. And the idea of following up near-Earth objects is to calculate their orbital parameters and determine whether these are a threat to the Earth, basically. So since we fully automated our 1-meter telescope, so you may remember I said at the beginning of the talk that this telescope is now so automated that you don't even need a human to submit an observation request to it. And the other thing is, you remember I said at the beginning, there's another telescope in this empty space here, and it's a telescope that's part of the NASA Atlas network. So NASA have a world network of 4 telescopes around the world, and the purpose of those telescopes is to look for near-Earth objects. So those NASA telescopes are the discovery machines. But it's one thing to discover new asteroids or new objects. It's then another to calculate the orbital trajectories of those objects. For that, you need more follow-up observations to see how the object is moving through space and then calculate the orbital parameters. So what we've set up here is, once the NASA telescope has discovered something, and it does that automatically, it analyzes its images and sees and calculates to see if there's anything new in that image. If there is, it will then automatically submit an observation request to our LSADI telescope to follow up on that object to see how it's moving through space and then to calculate its orbital parameters. And since this was activated in 2023, since 2023, we've actually triggered on 145 new near-Earth objects. 88 of them were successfully robotically observed with our 1-meter telescope. And of those 88, 71 of them were then new objects that were officially then part of the MPEC. I can't remember what MPEC stands for now. It's Minor Planets something committee. I don't know, part of the International Astronomical Union. So this LSADI telescope was automatically, robotically, without any human interaction, was able to discover 71 near-Earth objects. So if you've ever seen the movie, what is it, Don't Look Up, or Look Up or something, it's a Hollywood movie that came out a few years ago about the followed an astronomer who discovered an object that was coming to hit Earth and end all life on Earth. It's a very high probability that if there was a object about to hit Earth, there's a high probability that the news would come from this telescope, because this is one of the telescopes that calculates that's responsible for formulating the exact orbital parameters of these objects. And here's another example of, as a result, that we can now fully automate this telescope. So I don't know if you remember, but a few years ago, 2 years ago, there was the DART mission. So this is the mission that NASA, it was a NASA space mission where they basically collided a spacecraft with a known asteroid. And the idea behind this project, behind this NASA project, was to see, could they alter the trajectory of this asteroid by slamming a spacecraft into it. And because we knew exactly when this impact was going to happen, we could automate our telescope to locate the asteroid and at the time of the impact. And we took a series of images just to see what we could see. And you can see we captured the explosive material that came off the asteroid as a result of the NASA spacecraft slamming into it. So that was a nice publicity stunt there. I don't think anyone was expecting that we would be able to see from Earth the kind of explosive plume of dust that comes off the asteroid. So that was a really nice result for our new autonomous telescope. So another example, another science result is that we're now also able to follow up on what are called gravitational microlensing in events. So if you're not familiar what microlensing is, so this is a prediction made from Einstein's theory of general relativity, where gravity can bend light. So, as you know, light generally travels in a straight line, but general relativity also predicts that light can be caused to change direction in a strong gravitational field. So in astronomy, we can take advantage of this in that a far-off source star, its light can be lensed by a gravitational lens so that the light from that source star gets focused on the Earth. So you can imagine this requires a very accurate alignment of a source star and a foreground star for that light to be focused. And what usually happens is, in these microlensing events, is this foreground star is actually too dark. You can't actually see it. So there's an unknown mass where if it passes in front of a source star, this source star can suddenly become quite bright. I think I'll jump the slide there. So here's an example of a microlensing event. So this is the background star, and an invisible foreground star passed in front of it. So this is a time sequence. So here you can see how the brightness of that background star increased as the foreground invisible mass passed in front of it, went through the middle, and then disappeared off to the side. And this technique is being used to discover planets in other systems. So in this case, okay, if there was just this one peak, that kind of indicates that the foreground invisible mass is just a simple point source. But what we look out for is little blips like this. And this indicates that perhaps this is an indication that that foreground invisible object also has a planet orbiting around it. So we can model these light curves and determine the mass of the foreground invisible object, but also the orbital parameters and then perhaps the masses of that hidden planet as well. So that's exactly what we've done with our automatic telescope. Instead of now, constraining our observations to fit in 1 week, we can now spread out our observations over several months. So this is one microlensing event that we monitored over a few months from February to May last year. And you can see, so there's 3 colors here. So this is just photometry in 3 different filters. But you can see how the light curve over a few months kind of followed this kind of rise in intensity, then a dip, then a double dip, and then it went back down to its normal brightness. So this was a very interesting system because this kind of double high increase in intensities, the double peak, is an indication that the foreground invisible system is a binary system. But also you can see here, there's some data gaps here, but there is another peak in the light curve before the main double peak. So this looks like we've discovered a planet orbiting a binary system in this system. And we wouldn't have been able to do this before until we now allow this mode of just taking snapshot observations every night the weather's clear over a period of several months. Okay, this is a rather busy slide, but this is my final slide. So this is a good example of how we can use all of our facilities in Sutherland in combination with our international partners and national partners to do world-class astronomy. So this is part of a so-called multi-wavelength campaign. So this is the discovery of a new class of object. It's one of these white dwarf pulsars that I sort of introduced to earlier. But the key thing here is that we were able to, the upper plots are radio light curves from Meerkat in South Africa. So you can see as the radio observations go along, it shows these blips, if you like, very rapid increases in brightness. And these are actually occurring on a 3-minute time scale. So you can see here, this is the same data set, but folded and binned on this 3-minute time scale. So you can see that this system is kind of a radio pulsar. Every 4 minutes, there's a radio pulse from this system. At more or less the same time, this might have been exactly at the same time, actually, we were able to get high-speed imaging photometry from our 1.9 meter telescope. So at the same time, we were able to see these high-frequency pulses that are also occurring in the optical regime. Then at another time, these rather complicated plots are plots of the high-speed photopolarimetry from the 1.9 meter telescope. So we were able to show that these pulses are actually highly optical polarized. And then together with our international collaborators, we were also able to get X-ray observations using the XMM European Space Agency telescope. And that was also showing X-ray pulses at this 4-minute time period. So these 2 papers came out last year. There was an Astronomy and Astrophysics that described the X-ray data, and there was a Nature Astronomy paper as well, where we put all these observations together. So this is a really cool example of how, now we've moved forward, that we're able to very quickly respond to new discoveries, but also we're able to, in combination with our national partners and our international partners, to obtain observations over a multi-wavelength. Oh, sorry, I didn't mention this one as well. This is a salt-trailed spectroscopy. So this is showing how the H alpha line was showing this kind of strong pulsed behavior. Okay, I think I've spoken for quite a long time there, so I think I'll stop there and happy to take some comments or questions.
Thanks very much for a fascinating talk there, Stephen. It's very interesting to see how automation can contribute in an entirely new way to astronomy and science. So
Thank you.
we look forward to some. Peter Harvey has got his hand raised. Would you like to go ahead, Peter? Peter, do you want to ask a question?
Okay, yes, sorry. I couldn't get my mute button to unmute. Thanks, Derek. Stephen, just a couple of questions here. One is, you talked about that instrument selector port that you developed last year, or whenever it was, you said. Is that unique in the world, or do other telescopes have it?
Yeah, other telescopes do have it. But you generally have to custom make them to fit your telescope and your particular suite of instruments. So it's not something that you can buy off shelf. They have to be custom made. So that's why it was all designed and manufactured in-house as well. So it was so not only was it, we also had to include in it a new auto guiding mechanism as well, so that both instruments could use the auto guiding mechanism. So it's kind of, the instrument selector port was to allow the addition of an additional instrument, but also it had a auto guider mechanism included with it as well, that both instruments could use.
Okay, thanks, Stephen. And the other question was, you talked about the time slots that you sort of allocated a week or something like that, whoever wants to use it. If you get clouded out over that time, you've lost your time slot, right? Is it difficult to get another time slot?
Yeah, exactly. So that was the old way of doing it, and we still allow that. But then, you know, the observations are there at your own risk. You will get allocated a week. You don't have a choice of when that week will be allocated to you. You can say in which, say 3 months, you want to use the telescope, because it has to be the right season for your particular targets. But where in that 3 months your week will occur depends on many other factors, like who else has applied for telescope time as well. So you will be allocated that 1 week. And of course, then who amongst us can arbitrarily give up 1 week to travel to Sutherland? And then you're right. If the weather's clouded out for that whole week, that's it. Your time is lost. All you can do is apply for time again next year and hope for better weather next year. But if instead you submitted your observation requests to the automatic telescope, it goes into the queue. So then your observation will just eventually get done. It's just waiting in the queue. The telescope only observes when it's good weather, obviously. Your observation is not given a specified date. Instead, it's just given a queue, and it will eventually get observed. So you can imagine how much money, particularly overseas visitors, would save by not having to travel to Sutherland. And then even worse, they travel to Sutherland and the weather's bad and they go home without any data. They spend all that money to get here.
Sure, it's a bit of a risky lottery, isn't it?
It is. Astronomy's always been
Yeah.
like that. If
But I
observational
suppose
astronomy.
Sutherland is pretty reliable for weather, isn't it?
Yeah, it's depends on what time of year. I mean, obviously summer is better, but the nights are shorter. Winter is more risky, but when you have good weather, you have very long nights, so you can get lots of time on the telescope. And I can tell you now, the observatory has been closed for the past 9 days because of this weather systems we've had coming through. I mean, that's more than usual. That is more than usual. We're not usually closed for maybe 10 days in a row. It's quite extraordinary at the moment.
Thanks, Stephen.
I see Elaine had a hand raised, and Pierre also has a hand raised. But Elaine, do you still want to ask a question?
Yeah, that was me, Derek.
Oh, David.
Yeah, Stephen, thank you very much. That was very interesting. Just on a sort of practical availability of the whole system through a year, you have to obviously have time out for maintenance and for the upgrades that you've undertaken. That's one question. And the other one is, how do users of the system pay for the time they request?
Okay, that's great questions. So in terms of maintenance, so those 3 telescopes, they're generally available all of the time. Any maintenance, I mean, this is one of the great things about astronomy is that the equipment gets used by the researchers at nighttime. The maintenance people do their maintenance in the daytime when the astronomers don't need to use the equipment. So there is ongoing maintenance, but that's all done during the day by the technical crews. So sometimes there may be a technical fault that results in a breakdown that could take the telescope offline for a night or two, but they're quite rare, actually. The telescopes are generally available all the time, provided the weather is good. So yeah, the next question was about was paying for time, right? So
how's the whole all your work funded, and how do people pay for the time they use?
Okay, so that's 2 different questions. So we're a national facility, so we're here to provide a service to whoever wants to use the telescopes, and we provide that for free. So what happens is, if your science program is approved to use on one of our telescopes, you can use our telescopes for free. We do not charge for time on our telescopes. If you want to travel to Sutherland and spend time in Sutherland, then we'll obviously charge you for the cost of staying in the hostel for accommodation and food, but we don't charge for telescope time. And that's generally the case internationally as well. For other institutes, other observatories around the world, those observatories that open time to the whole community on a competitive basis, if your scientific program was better than everyone else's and you got time, you get it for free. There are obviously other observatories that are more specialized and private, and they have different business models, so you can purchase time on them, and in which case they don't particularly care so much about what your science is, because you're paying for the time and therefore the risk is yours. For an observatory like ours, as I say, we don't charge you, but your science is on a competitive basis with everyone else's. So through that system, we get to ensure that the best science gets done on our telescopes. And then in terms of funding to operate the telescopes, where the South African Astronomical Observatory is a national facility, it's part of the National Research Foundation of South Africa. So it's a government aid. The National Research Foundation of South Africa is a government agency for the funding of the national facilities. The SAAO is one of 4 or 5 national facilities. There are other facilities around the country, that the NRF funds. And the National Research Foundation is actually an agency under the Department of Science and Innovation. So we're a purely, we are a government-funded agency. But you'll also remember from the beginning of the talk that a lot of those telescopes are telescopes that we operate in partnership with other international institutes. So those telescopes are generally funded by the international institutes, and we take up the cost of operating them or maintaining them, and providing electricity and internet and that sort of thing. It depends on the particular telescope, but that's how all the other telescopes generally get financed, is through international partnerships.
Great, thank you very much.
Pierre de Villiers had a question. Pierre, if you want to go ahead.
Stephen, thank you very much for a very interesting and I think a very well presented talk. It was most enjoyable.
Thank you.
I remember just after COVID, Petri Vasonen was our guest speaker. I think that's just the early days when we started to have Zoom meetings. And he was very proud of the fact that SAAO was one of the first observatories to become operational after COVID. And in his talk, he also mentioned that the SAAO was planning to turn SAAO into an intelligent observatory. So that's the first time that I heard, or that we heard, that term. And I must congratulate you on the success that you've obviously achieved. The response times of your instruments and the data are absolutely baffling. How many other intelligent observatories are there worldwide? And please beware against excessive modesty. How do you rank against the others?
Well, thanks for the compliments. I really appreciate it. We did work hard for this, so it's good to be appreciated like that. So I guess the Intelligent Observatory was a phrase that Petri Vasonen, our previous director, he coined that term. So we had this upgrade program, but he put it all together and made it an Intelligent Observatory, a package to describe our development path. So I think we are quite unique in this way, because there are other automated and robotic telescopes around the world. There's no doubt about that. They've been around for a decade or 2 decades. The first ones came online. But those telescopes are generally singular telescopes that operate on their own. And they tend to be dedicated, for example, survey telescopes. So they operate very simple programs of scanning the skies every night with wide field cameras to survey the whole sky, maybe in different filters and things like that. So they're dedicated single science surveys. What's unique about us is that we're trying to better combine all the telescopes that we have in Sutherland. And so this is where we've become very unique and successful in what we're doing. So the examples that I gave, for example, the NASA Atlas telescope, having that robotically linked to our telescope on site. No one else has done that. There's another telescope that I forgot to mention. It's the telescope that we have in collaboration with an institute in Holland. It's called the Meerlicht telescope. So this is an optical telescope we have in Sutherland, and its job is to look at whatever the Meerkat telescope is looking at. So Meerkat is doing radio observations of the sky, and the Meerlicht telescope is getting the live coordinates of where the radio dishes are looking at. The Meerlicht optical telescope is looking at the same part of the sky. So it's getting simultaneous optical observations with the radio observations. So it's slave to the radio telescope, as it were. But then the Meerlicht telescope if something interesting happens in the radio sky, and if there's an optical counterpart, the MIRLIC telescope will then communicate with our 1 meter telescope to say, there's something interesting here, will you follow up with more detailed observations? And we will then take over with, you know, longer photometry or spectroscopy, because MIRLIC then will then look somewhere else because it will go wherever the radio telescope is going. But if it discovers something interesting, then we follow that up as well. Yeah, so we're very unique in doing that, in being very fortunate that we have multiple telescopes from multiple institutes around the world. And because of our geographical location on Earth in Southern Africa, you know, many institutes around the world want to put their telescopes here. And so we're very careful in when we form the agreement or a memorandum of understanding between us and the foreign institute. We make sure that that telescope is able to be incorporated into our Intelligent Observatory. The mode at which it observes, we can make use of. So that's definitely unique. There's nothing like that in the world at the moment.
Thank you. You make us proud to be South Africans.
Absolutely, yeah.
So just to at the moment you have the 3 telescopes.
Yeah, so those 3 telescopes are our fully owned core telescopes. So that's,
and you're going to expand to other telescopes at some stage, including maybe SALT.
Well, SALT is already Q scheduled. So it is part of the Intelligent Observatory in that it's not a robotic telescope, but it does operate a Q scheduling system. So if there's an opportunity of an interesting event happening, we can submit observations to the SALT telescope or any of our other telescopes as well. So SALT, in a way, was already ready to be incorporated into the Intelligent Observatory. So it's operated with service observers rather than being robotic.
I think you've frozen there for a second.
Yeah.
Stephen, sorry, you froze there for a second. So is there no chance that you say SALT is operated by people at the telescope, but the astronomer might be remote?
Yeah. So yeah, the astronomer doesn't operate SALT at all. It's operated by local expert SALT astronomers.
Okay.
And what they do is they follow a queue of observations. So the astronomers would submit their observations to the queue, and then the expert astronomers would execute whatever's in the queue. So in a way, that's how it's part of the Intelligent Observatory, is that we can autonomously submit proposals, observation requests to the SALT queue.
Okay.
So it's not a robotic telescope, but we can define what the queue is automatically, and it will, instead of a robot operating the telescope, there's a real human. But as far as the external astronomers concerned, they don't know the difference. They just know that their observation got into the queue.
If there isn't another question at the moment, I've got another quick one. Has there ever been any sort of interest or consideration of putting up any of these massive telescopes that are going up in Chile, in Sutherland, or is Chile just a better location for those?
Yeah, Chile is definitely the best. Yeah, Chile is definitely the better site. The mountains there are twice as high, so the air is a lot thinner. Yeah.
Less distortion and so on.
Less distortion. I mean, we're still so the Sutherland site is quite comparable in terms of darkness. It's a very dark site.
Yes.
Well, we're just as dark as the best observatories in the world. But the big new telescopes are coming along. They want, one of the requirements is just for sharper, clearer images. So their telescopes are designed where they need sharper, clearer images. Our instruments and telescopes are not designed to take advantage of superb image quality, but they are designed to take advantage of the very dark skies. So that's why, for example, spectroscopy is a great mode to have in Sutherland.
Is there any benefit in using a group of telescopes there simultaneously to sort of get a better resolution on the same target?
There's definitely an advantage to using multiple telescopes, because then what you can do is one telescope can be doing imaging, one could be doing spectroscopy, and another one could be doing polarimetry, all at on the same source.
Yeah.
So that's the advantage there, the kind of different ways that you can observe a target. But that's something that is unique to the observatory, right? In general, the one-user telescopes, the single telescopes elsewhere in the world have single instruments. But we have a different variety of instruments, so we can simultaneously do that. We can't really combine them to improve image quality. That requires kind of optical interferometry.
Yes.
And that's extremely difficult to do. There's only a few telescopes around the world that can do that, and they do it very rarely. Actually, it's a very difficult thing to do, optical interferometry.
Okay.
It's easier with radio. That's why we can do it with radio. The wavelengths are a lot longer, so it's a lot easier to combine those radio waves. But to do that in the optical, yeah, that requires a lot of difficult technology.
All right. Do we have any more questions for Stephen from the audience?
Yes, Peter. Yeah, Stephen, I'm just curious to know, how do you determine the scientific merit of a project proposal, and what is the success rate of all these submissions?
Yeah, that's a good question. So we have what's called a time allocation committee. So it's a committee of about 4 or 5 astronomers, and it can be a different group of astronomers at any one time. And there's only maybe 1 or 2 astronomers from the observatory on the committee. We generally ask for astronomers, 1 international astronomer and maybe 2 other astronomers from another institute in the country. So they sit on the committee, and they independently, what they do is they independently read all of the proposals, and they independently rank them, and then they get together and compare their rankings and come up with a final ranked list of scientific programs. So that works quite well, because in general, everyone kind of agrees what are the greatest proposals. The best proposals usually shine out quite obviously, and they generally agree on which are the worst proposals, and then there's kind of a mixture in the middle. So then sometimes we're oversubscribed. So sometimes we have the number of proposals we have, and the total amount of time that's asked for is more than the time is available on the telescope. But generally it evens out about 1. But yeah, sometimes we're oversubscribed. And we are becoming more subscribed now, because it is now a lot easier for people to use our telescopes. Before, when you had the only way to use our telescopes was by traveling to Sutherland, that rules out pretty much 90% of astronomers. They simply don't have the time or the money to travel to Sutherland to use the telescopes. As soon as we went to remote observing and now autonomous observing, our telescopes are now used every clear minute of the night, every clear minute of the night time sky. Sorry, that was a mouthful.
Thanks, Stephen. And just another question: how would James Webb contribute to your observing campaign at Sutherland?
Yeah, that's a good question. So that's a very specialized telescope as well. It's obviously in space, so it does the image quality from that is absolutely amazing, and our images would never compare to that telescope. So there's no point in us trying to compete in image quality. But we can do things that telescope can't do, which is optical spectroscopy and polarimetry modes and high-speed photometry. So there are cases where we can complement the science that the James Webb Telescope does. And sometimes as well, the James Webb Telescope makes new discoveries. So sometimes it will find an object that was not there before. And it won't continue observing that new discovery because it was a serendipitous discovery, a new random discovery. It's not part of their program, but they will announce it as an alert that, hey, you know, we've discovered a new discovery. So then we would follow up on that new discovery with observations from our telescopes, more detailed observations to work out what that new discovery actually is.
Thanks, Stephen.
Even I'm quite amazed to hear that you don't charge for the telescope time. When I've used the iTelescope system when they've given some free time for a while and so on. But I mean, for me to go and pay, 50, 100, 200 euros, whatever, for an hour on a telescope is just too much. If you had to charge your actual cost per hour, I should imagine it would actually be quite high. But was there ever any consideration or thought of actually charging for some of the time?
Yes, so that is actually a possibility. Well, not on those three telescopes, but the SALT telescope, the Southern African Large Telescope. So that telescope is financed by a consortium of partners. So South Africa has the largest fraction of time on that telescope, and then there are other institutes from around the world in the US and Europe and India. I think they're the three main countries, three main countries that are partners in the telescope. So those institutes fully fund the telescope. And so they basically paying for their time on the telescope by contributing the yearly cost of operating it. But on SALT, we also sell time. So there are two ways of getting time on the telescope. You can be a member of one of the partner institutes, and you can apply for time through their competitive application process. So here in South Africa, for example, anyone is permitted to apply for time, and if your scientific idea is rated good enough and better than most of the others, you will be awarded time for free. But we also sell time, and I don't know how much it is, sorry, but I think it's quite a bit more than a few €100 per hour.
Yes, it would be.
Yeah, so it is, you can purchase time on SALT as well.
All right, fascinating. And really gratifying to hear that we're contributing in such an innovative way to science and to astronomy.
Yeah, you take advantage of your niche area, right? You figure out what it is and try to go with it. Yeah.
Fantastic. Any more questions for Stephen? All right. If there's no more, then I want to thank you very much for your talk. Fascinating and very good. So
thank you for inviting me and asking your questions. I really appreciate it.
it's all recorded, and I'll send out the links in a day or two.
Great.
And yeah, thanks very much for everything.
Well, thank you.
We hope to have
Okay.
you again sometime.
Thank you. Good night.
Yeah. Good night, everyone. Bye-bye.
Yeah, thank you. Good night.
Good night,
Yeah,
Stephen.
thank you very much.
Thank you. Night.
Thanks everybody for attending. I'll be signing off. Thanks, Stephen.
Lovely. Thanks again. Bye.
Looks like it.